Okay, let's just jump right in. Right now, as engineers work to design this totally massive electrical bridge connecting the power grid of Saudi Arabia with the power grid of Egypt, they aren't just out there laying cables. They're actually fighting an invisible, incredibly powerful force that quite literally divides our modern global infrastructure. See, Saudi Arabia operates on a 60 hertz standard, but Egypt, they operate on 50 hertz. So, welcome to this explainer, where we're going to unpack exactly what happens when these two massive, completely incompatible systems collide. We'll find out why something as small as 10 cycles per second literally changes the physical laws of our electrical world. Here's our quick roadmap for the explainer today. 1. The global frequency divide. 2. Heavy metal, looking at power transformers. 3. Need for speed with induction motors. 4. The long haul for transmission lines. And 5. Playing by the rules.
All right, let's get into section 1, the global frequency divide.
Now, global adoption is incredibly uneven. You might logically think grid frequencies are a 50-50 split, right? But actually, roughly 80% of the world, which includes Europe, Africa, and most of Asia, runs on a 50 hertz grid. Meanwhile, just 20% of the globe, primarily the Americas, Saudi Arabia, and a few parts of Asia, operate on 60 hertz.
And honestly, what does that massive divide actually come down to? 10, just 10 hertz. That is a mere 10 alternating current cycles per second. I mean, it sounds like a rounding error, doesn't it? But as we're about to see, this tiny 10 hertz difference is literally the only barrier standing between these two giant systems, and it alters the electromagnetic and mechanical behavior of power equipment in ways that will completely blow your mind.
Moving right along to section 2, heavy metal power transformers.
Okay, don't let the math scare you. Let's de-jargon this EMF equation together really quickly. This dictates the design of a power transformer. E is your voltage, F is frequency, N is the number of wire turns, and phi m is the maximum magnetic flex. I want you to think of frequency like a lever. When you pull that frequency lever up, let's say from 50 to 60 hertz, the need for maximum magnetic flex to achieve the exact same voltage actually goes down.
And this leads us to our very first real-world physical consequence. Because a 60 hertz system needs less magnetic flux, the physical iron core of the transformer doesn't need to be nearly as big. They can be manufactured to be smaller, lighter, and way more cost-effective. But on the flip side, a 50 hertz transformer needs a lot more iron and copper to prevent magnetic saturation, making it noticeably bulkier and a whole lot heavier. All right, section 3, need for speed induction motors. So here is the absolute rule of the road for alternating current motors. Their speed is entirely locked to the grid frequency. The synchronous speed of a motor is calculated by taking 120, multiplying it by the grid frequency, and dividing it by the number of poles in the motor. So let's do the math super fast. A standard 2-pole motor on a 50 hertz grid will run at exactly 3,000 RPM. But take that exact same physical motor and plug it into a 60 hertz grid, it instantly spins up to 3,600 RPM. Think of the 60 hertz grid as a sprinter. By simply operating on a higher frequency, industrial plants get an automatic 20% speed boost from the exact same physical motor footprint. So what does that mean for us? It means higher output from centrifugal pumps, much faster moving factory conveyor belts, and significantly more air being pushed through commercial HVAC cooling fans. But as we all know, speed isn't everything. Let's contrast our 60 hertz sprinter with the 50 hertz grid, which really acts more like a slow and steady marathon runner. Lower operating speeds on a 50 hertz system mean a lot less mechanical stress. It reduces friction, it puts significantly less wear and tear on the motor's bearings, and it ultimately extends the physical lifespan of all that rotating equipment. So you're essentially trading that 20% performance boost for essential longevity and long-term reliability. Now, here is where we hit what I like to call the rule of unexpected consequences. If you take a centrifugal pump designed specifically for a 50 hertz system and naively just plug it into a 60 hertz grid, you don't just get 20% more power consumption. Oh no. According to the affinity laws of physics, power consumption increases by the cube of the speed ratio. That is a literally massive power spike. If you move regions, you have to completely recalculate your variable frequency drive parameters and literally shave down your pump impellers, or honestly, you will burn your equipment right to a crisp. Zooming back out, let's hit section 4, the long haul, transmission lines. Whenever we send alternating current down really long wires, the transmission network creates natural resistance, specifically what we call inductive and capacitive reactance. If you look closely at these formulas, frequency does two totally different things. In inductive reactance, it's a multiplier, but in capacitive reactance, it's a divider. This means they behave entirely oppositely when you tweak that frequency lever up or down. And when we pit the two grid standards head-to-head out in the real world, 50 Hz comes out as the clear, undisputed champion for the long haul. A lower frequency yields a lower inductive reactance, which directly translates to a much better, far more stable voltage drop profile over massive distances. 60 Hz really suffers here. Its higher inductive reactance means much larger voltage drops, which basically forces utility companies to either build substations closer together, transmit at dangerously higher voltages, or install extremely expensive capacitor banks just to keep the power stable. 50 Hz also firmly wins out regarding something called the skin effect. See, in alternating current systems, electricity doesn't actually flow evenly through the whole cross-section of the wire. It desperately wants to ride along the outer surface, or the skin of the conductor. And the higher the frequency goes, the worse this effect gets. Because 50 Hz is lower, the skin effect is less pronounced, which allows electrical engineers to utilize the entire area of that super expensive copper or aluminum wire much more efficiently.
Finally, let's wrap up with Section 5, Playing by the Rules, Codes and Compliance.
Now, I really want to slow down here for a second to emphasize just how catastrophic a mix-up can be. Remember our math from earlier? If you try to take a smaller, lighter 60 Hz transformer and hook it out to a 50 Hz power grid without radically derating the voltage, the lower frequency instantly increases the magnetic flux way beyond what that smaller iron core can handle. The core will magnetically saturate, it will violently overheat, and it will absolutely fail. Because the physics here are just totally unforgiving, our control systems are built to be absolutely ruthless. Modern grids are constantly monitored by SCADA systems and protective relays, like the ANSI 81. These things must be explicitly programmed for the exact base frequency of the region. If a 50 Hz programmed relay even briefly monitors a 60 Hz system, it registers that frequency as a critical system-ending anomaly and commands an instant trip, shutting down the entire system to protect it. There is literally zero margin for error. This physical divide creates an incredibly complex nightmare for the global supply chain. The International Electrotechnical Commission heavily leans toward 50 Hz, which makes sense, since they serve 80% of the globe. But if you're building in Saudi Arabia, the Saudi Electricity Company strictly enforces 60 Hz codes. Sourcing specialized European equipment for Saudi projects means dealing with agonizingly long lead times. Thankfully, though, modern solid-state electronics and smart variable frequency drives are increasingly able to artificially bridge this gap, taking in one frequency and smoothly outputting exactly what the equipment needs. And that brings us right back to the future, and to the question we started with. We began by talking about that massive bridge between Saudi Arabia and Egypt, a 60 Hz grid meeting a 50 Hz grid head-on. As our global grids increasingly interconnect to share renewable energy across borders, how will the next generation of engineering innovation continue to bridge this invisible 10 Hz divide? It's a colossal challenge, and one that absolutely proves just how profoundly the smallest of numbers can shape our entire physical world. Thanks for joining me on this explainer, and keep questioning how the world around you is wired.